Welcome, everybody, to our first inaugural virtual forum from Mandala Space Ventures. My name is Leon Alkali. I'm the founder of CEO of Mandala Space Ventures. We're located here in gorgeous downtown Pasadena, and wanted to welcome you all. We'll get to our speaker right away. I'm delighted to welcome my good friend and colleague, Jason Rhodes from JPL. And Jason, before I hand it over to you, I just want to give a little rationale for why you're here. It is not obvious to the casual observer that a topic like dark matter, dark energy, and exoplanets is what Mandala Space Ventures is all about. But I want to explain that because it really is a perfect fit. And I think having you as our first speaker is just amazing, and it's so cool to have you here. Mandala Space Ventures is a Pasadena-based space-themed venture studio. We invest and we create new startup companies in the emerging space ecosystem. In my experience, a lot of our investors, a lot of our friends, one common theme amongst all of them is that they're curious about space. They want to know. They want to know about science. They want to know things that are not necessarily all about investment and dollars and cents and VCs and so on. So I feel that part of our ecosystem, part of our community that we're trying to build really cares about deep scientific topics when it comes to space. Dark matter, dark energy, exoplanets, wow, what a cool topic. And the fact that we have you here as a friend visiting us at Mandala Space Ventures is just amazing to me. I want to thank you for being here. And I think the audience for sure is in for a treat. I can assure everybody who's listening to this now or as we record it maybe in the future, that by listening to your presentation, you will undoubtedly learn something about dark matter, dark energy, and exoplanets. And just enlightening people about this topic, I think will make everybody more understanding, more appreciative of science. And certainly that's part of our mission at Mandala Space Ventures. So with that brief introduction, again, welcome to everybody. And I'm turning it over to you, Jason. Take it away. Let's learn about dark matter, dark energy, and exoplanets.
Thank you, Leon. That's a fantastic introduction. I'm really excited to be the inaugural speaker here. So I'm hoping that everyone online can see my screen. We're good? Okay. So I'm going to talk about dark matter, dark energy, and exoplanets, as Leon mentioned. And I'm going to give you an intro to those topics and talk about how a new telescope that we're developing at NASA called the Nancy Grace Roman Space Telescope, which we hope to launch in about 4 years, is going to tell us a lot about these really exciting topics. And I want to give a special thanks to one of my colleagues that helped me come up with some of these slides and the messaging here, Dr. Alina Kiesling. She's actually here in the audience. She's a fellow astrophysicist at JPL with me. So I acknowledge her input into this talk. So I'm a cosmologist, which means I study the universe as a whole. And any good cosmologist starts off a talk with what we call the pie chart. So this is a pie chart of the universe. And you'll see that the pieces of the universe in this pie are not very even. So the normal matter, that is gas, dust, stars, everything that we can see makes up about 5% of the universe. And most of that is in gas and stars. And a little tiny bit is in neutrinos, these ghostly particles, about a billion of which pass through every square centimeter of your skin every second of your life, but you hardly ever interact with any of them. You never feel them. So they're a tiny component of the universe. And you'll notice that one of the things that I'm going to talk about later today, exoplanets, which are planets outside of our solar system, they don't even show up on this pie chart because they're such a small component of the universe. They're small, but they're exciting for a few reasons that I'll talk about later. We've known for about a century now that most of the matter in the universe was invisible to us and we could only detect it gravitationally. And I'll tell you about how we do that. And we call that matter dark matter. And we've known for about a quarter of a century now. In fact, it's a quarter of a century this month that two important papers were published that showed the biggest component of the universe is dark energy. And dark energy is causing the expansion of the universe to accelerate. So I'm going to talk about all these different components of the universe and how we study these different components of the universe today. We don't know what these are, dark matter and dark energy. They're very mysterious. They're 95% of the universe. And that's what's motivating a big part of this Nancy Grace Roman Space Telescope. And it's motivated my 20-some year career in astronomy and astrophysics at JPL. So let's start here. Let's talk about dark matter and how we know about dark matter. Well, I'm going to talk about a brief history of dark matter. And the first sort of inklings of dark matter started in the 1930s with an astronomer named Fritz Zwicky, who worked over here at Caltech. And I'm pointing literally at Caltech as I sit here in Pasadena. And what Fritz Zwicky noticed was that when he studied galaxies, he looked at the motions of galaxies. And we knew the equations of motion from the time of Newton, how things should move, an object in motion stays in motion, and so on. And what he found was that the motion of these galaxies couldn't be explained by the weight of the galaxies, the mass of the galaxies, if the only thing in the galaxies was the visible matter, the stars, and the dust. So there had to be more stuff there. So fast forward about 30 years, and in the 1960s, a pioneering astronomer named Vera Rubin was studying the rotation of galaxies. And I'm showing here an artist's representation of a rotating galaxy. This is a spiral galaxy like our own Milky Way galaxy. And what you see there is there's lots of stars, gas and dust in the center of the galaxy, and it becomes much less dense as we go toward the outer edges of the galaxy. And the equations of motion would indicate that as you go towards the edge of the galaxy, the rotation velocity, that is how fast the galaxy is rotating, should trail off. And that's what's shown in this plot. So they expected, Vera Rubin expected to see the trailing off of this rotational velocity as a function of distance from the center of the galaxy. But instead, what she found was that the actual velocity of rotation of the galaxy was pretty constant across the whole galaxy. And what that indicated to Vera Rubin at the time was that there was dark matter in this galaxy. That is, the trailing off of the matter that we see just by looking at the visible matter isn't what's happening. And there's more mass in the outer edges of galaxies than what we can see. And she called that dark matter.
Was she the first to coin that phrase, or?
I think the phrase had been coined already, but she did the first work that we now consider to be the first work that really showed strong evidence for dark matter. And she passed away a few years ago, having not won a Nobel Prize. And a lot of people in astronomy and physics think it's one of the big travesties of the past century that she didn't win a Nobel Prize for this work. So I'm going to talk a little bit about the growth of structure in the universe and the growth of the universe. What I'm showing here is a baby picture of the universe. This is the earliest known picture of the universe. In fact, it's the earliest possible picture of the universe. This is a picture of the microwave background as seen by the Planck satellite. This is a picture of the universe about 300,000 years after the Big Bang 13 billion years ago. So in the very earliest stages of the universe. And the reason this is the earliest possible pictures of the universe is that before this, the universe was opaque and we don't see light from before this time in the universe. But what you see in this picture, which is really a heat map of the universe at that time, is hot and cold spots, red spots and blue spots. And those hot and cold spots correspond to overdensities, places where there's more stuff, and underdensities in the early universe. And this is a very exaggerated picture because the overdensities and underdensities in the early universe were only different by about 1 part in 10,000. So it was almost a completely smooth universe. But we do see these overdensities and underdensities, and the overdense regions grew through a process called gravitational instability. Now that's a big term, but it's pretty simple to think about, and that is where there's more stuff, there's more gravity, so you accrete more stuff. And so the dense regions over time become more and more dense. And so what we see today, and this is a picture taken with the Hubble Space Telescope about a decade or so ago. This is a very deep picture of the universe in a very tiny spot on the sky. And every single spot of light you see there is a galaxy like our own Milky Way galaxy with hundreds of billions of stars. So we see an unbroken line between the very early universe, where there were these small fluctuations in density, to the huge fluctuations in density we see today and the formation of galaxies and clusters of galaxies that we measure today. But keep in mind that when we're looking at this picture of the galaxies, we're only looking at the tip of the iceberg. We only see the visible matter of the galaxies. And we know that most of the matter in those galaxies is the dark matter. Much like when we see an iceberg, we're seeing the part above the surface of the ocean, but most of that iceberg is invisible to us below the surface of the ocean. So the question is, how do we detect and how do we see this dark matter? So
Jason,
I'm
I
going
have
to take,
a question. If the analogy with the iceberg is the way you bring it up, is the dark matter particularly associated with the galaxy, or can the dark matter be anywhere else?
So in fact, that was one of the big questions that we had until about 15 years ago. And some colleagues and I, in a plot that I'll show you later, at Caltech, we did a study with the Hubble Space Telescope, and we did show that for the most part, the dark matter is in the same place as the galaxies. That's not 100% true. And so some people have asked me in the past, oh, how did that happen? And they say, did the dark matter follow the galaxies? And the answer is no. What happened is there were conglomerations of dark matter, and that's where the galaxies themselves formed. So it's the galaxies forming on top of the dark matter, and that is the galaxies that allow us to be alive, because that's where stars and planets form. So the dark matter, in a way, is responsible for the existence of galaxies, planets, and in that sense,
so this analogy with the icebergs is actually very, very,
it is
very good.
Yes, it is how we find this to be. And there are times when we can observe a displacement between the dark and the what we call luminous matter, the visible matter. And those form interesting ways of studying the dark matter in more detail. So I'm not going to go into that today, but sometimes there is a displacement, and there's always a reason for that.
Okay.
So I'm going to take a small digression and talk about the growth of structure in my life. So this is me at a conference on dark matter. And this is the earliest known picture of my relationship with my colleague here, Dr. Alina Kiesling. And you can see that like in the early universe, there was probably some slight attraction here, but it's hard to see because it wasn't so obvious in the early universe. It's not so obvious here. But if you fast forward, that structure did allow to grow. And 10 years later, we got married. And if I can pursue a little bit more the analogy, we've started to form new structures in the universe. And this is the newest structure that we formed a couple years ago. So this is
in this case, the attracting force was stronger than the repelling force.
For me, at least, and I think for Lena, yes. So this is our daughter, Blaze, and she's actually advertising here on her shirt the Roman Space Telescope. And so you'll see Roman Space Telescope spelled out there, but you'll also see an interesting pattern on the shirt. And so keep that in mind, because I'm going to come back to that pattern and what it means in a little bit. So that's the digression, but I want to now ask, how do we study the dark matter? We can't see it. It's invisible to us. It doesn't interact with light. It doesn't give off light. So how do we know it's there? So I'm going to show you a cartoon here. So what we have here is a distant galaxy. And when a cosmologist measures distances, we use this unit Z, or we call it redshift, but it's a unit Z. And so we're here at Z of zero distance from ourselves, obviously. And we want to view galaxies far away in the universe. And Z of 1 is a galaxy about a halfway to the edge of the visible universe. So Z of 1 is a galaxy that's very far away. So we don't use units that get very large in measuring the size of the universe. And it's to keep relatively simple math. So in the absence of anything between us and this distant galaxy, the light from the galaxy would take a straight path to us. And that's what I'm showing here. But we know that there's this ubiquitous dark matter out there in the universe. And I'm showing this on the slide as sort of a ghostly dark matter structure. And we're most sensitive to dark matter structures about halfway between us and these distant galaxies. And one of the properties of gravity, Einstein's theory of general relativity, is that mass bends space. Now, a lot of people have seen demonstrations of this with a sheet, maybe a rubber sheet and a ball, and the ball deforms the rubber sheet. Well, that's how gravity works with mass in space. And so the light, instead of taking a straight path to us, takes some curved path due to the bending of space. And what I'm showing here is a very exaggerated curved path. This isn't a scientific diagram. This is more of a cartoon. And instead of viewing the galaxy as it is there in the picture, we view the galaxy distorted. There's been some distortion in our image of the galaxy. Now, the galaxy itself wasn't distorted. It's just our measured image of the galaxy that's distorted. And so that's the effect that we're using to tell where the dark matter is. That distortion of the galaxy tells us that there's some dark matter there. So typically we have very weak distortions of the galaxy shape, and that's what we measure. But sometimes there's huge conglomerations of mass in the universe. And typically this happens where there's big clusters of galaxies. And I'm showing you here on the left side of the screen here, I'm showing you a cluster of galaxies. And there's a lot of galaxies there, but associated with those galaxies is lots and lots of dark matter. So the bright yellow spots are galaxies that are relatively close to us in this cluster. And this cluster acts as a lens. And what you see some faint arcs in the background of this picture. And those faint arcs are actually very distant galaxies that have had their images highly distorted by the foreground dark matter associated with this galaxy cluster. So instead of seeing them as little points of light, we see them as these arcs. And this is strong gravitational lensing, where we see a huge amount of change of the background galaxy shapes. Now, these strong gravitational lensing, I think, are typically one of the most favorite things for cosmologists to see, because they're really, really excellent images of what is happening with dark matter. And they're excellent laboratories to study dark matter. They're some of the best evidence that we have that there is dark matter. So these strong gravitational lenses typically make us very happy. And the universe has given us one, which allows us to show our happiness. So this isn't a Photoshop or anything. This is the universe giving us this happy face formed by strong gravitational lensing. So that's not the technique that I'm going to focus on here. I'm more focused on the weak gravitational lensing, because that happens in all directions everywhere we look on the sky. And the strong gravitational lensing happens only in specific regions where there's lots and lots of galaxies. So I'm going to use another analogy here to tell you about how we learn about dark matter with gravitational lensing. And I call this analogy a penny in the pool. Now, I live here in Southern California, pretty close to where we are now. But full disclosure, I don't actually have a pool. So this is actually a penny in my bathtub at home, but that sounds less sophisticated when I give this talk. So I call this the penny in the pool. And so in this analogy, the penny is like the distant galaxy. We can see it quite clearly here. And the water, which you know is there because you see distortions in the penny, the water is like the dark matter. You don't actually see the water, but you know the water is there. So if I look at this penny in my bathtub at home, I can see distortions. And that tells me a little bit about the water, because the penny, the light coming from the penny is taking a curved path through the water. And so I see it as distortions in the shape of the penny. Now, I don't know very much about the water in my bathtub by looking at one penny, but you can imagine if I threw 100 pennies in the bathtub, I could learn quite a bit about the properties of the water, how much it is, how dense it is, its temperature, and that type of thing. In the same way, if I look at 100 or 1,000,000, or in the case of a mission like the Nancy Grace Roman Space Telescope, nearly 1 billion distant galaxies, and look for those tiny distortions in their shape, I can tell an awful lot about the dark matter by looking at those distortions. And that's in fact exactly what we're going to do with the Nancy Grace Roman Space Telescope. So we've talked a bit about dark matter and how we're going to study dark matter. Now I want to talk about dark energy. What's this? And this is an even bigger mystery than dark matter. So let's go to the single equation that I'm going to show in my talk. And I always apologize. I know it's not a good idea to show equations, but this is, for what it represents, this is an incredibly simple equation, because what this equation represents is everything in the universe. This is what's called Einstein's field equation, and he came up with this equation just over 100 years ago. On the left side of the equation, we have gravity, which bends space and time, the G. And for the purposes of this, we can just ignore those subscripts, the mu and nu. On the right-hand side of the equation, we have two components. One is T, that's stuff in the universe, matter and energy. So that represents all the matter and energy in the universe. And when Einstein was coming up with this equation, people at the time thought the universe was static, not expanding, not collapsing, just a static universe. And the reason they thought that is that was the most aesthetically pleasing version of the universe they could think of. Not a great scientific reason to think that, but that's what they thought. And so what Einstein realized is that in a universe with matter, whether it's dark matter or normal matter, and gravity, it would want to collapse in on itself because gravity pulls things together. You know, that's how gravity works. So Einstein added this cosmological constant, this lambda on the right-hand side. And basically what this is this is just a component in his equation that he said, this is something that's holding the universe up from collapsing in on itself. So this, at the time, in the about 105 years ago, this is how Einstein described the universe. And this is the basis of general relativity, his description of gravity. And it's undergone about 100 years of tests, and we found it to be highly accurate in all cases. But nobody really knew what this cosmological constant holding up the universe was. But just a few years after Einstein did this work in the 1920s, a pioneering astronomer called Edwin Hubble was looking at distant galaxies and making measurements of those distant galaxies. And what excites me about giving this lecture here in Pasadena is this is a picture of Edwin Hubble at the telescope. And if I look this way, I have to lean about this much until I can see Mount Wilson, where Hubble did these pioneering observations. So we're just a very long stone's throw away from where these discoveries were made up in the mountains above Pasadena. So what Hubble did is he looked at these galaxies and he found that in all directions, galaxies were moving away from us. And the further they were away from us, the faster they were moving away. And that's what's shown in the plot on the right here. On the vertical axis is the recessional velocity, the velocity that a galaxy is moving away from us and always moving away, never towards us. And on the x-axis, that is the horizontal axis, that's the distance that the galaxy is from us. So what this showed is that the further away a galaxy was, the faster it was moving away. The only way to explain this is that the universe is expanding. And this sort of blew Hubble's mind and the minds of his contemporaries at the time. This was a big surprise because they had thought that the universe was static, not expanding or contracting. And so this was a discovery that sort of shook the foundations of cosmology because we no longer had the most aesthetically pleasing universe. Nature did not give us that. Nature gave us a universe that was expanding. So one of the things that excites me about this early work is that Hubble now, of course, has a telescope named after him. It's been observing for over 30 years. And one of the big projects it did is observations of these distant galaxies. And what I'm showing here, it's not quite the same units and measurement that Hubble was making, but very similar. This is a plot from now 7 years ago that shows a number of measurements of distant galaxies and how far they are versus how fast they're moving away. And it's really an exquisite confirmation of what Hubble showed nearly a century ago. And what's really exciting is if you took Hubble's early data, highlighted in pink, it would all be in the far lower left of this plot. So what the Hubble Space Telescope has allowed us to do It's expanded our view of the universe in a huge way by allowing us to look much further out in the universe than was possible with Mount Wilson up here, or indeed most ground-based telescopes even today. However, one of the things that happened is if you have an expanding universe, you no longer have to have this cosmological constant holding up the universe to keep it steady. So the cosmological constant wasn't needed to explain an expanding universe. And poor Einstein called this his biggest blunder. So this was Einstein's biggest blunder by his own admission, putting in this cosmological constant to explain the static universe, which turned out not to be static. Now, in an expanding universe at the time, sorry, let's go forward. An expanding universe at the time of Hubble, the thought was that there were two possibilities for the future of the universe. And what I'm showing here is just a cartoon going from the past to the future as you go from the bottom to the top of the page. So there were two possibilities. One was that we had an expanding universe that would eventually start collapsing in on itself. It expands for some time and then collapses. And the other possibility on the right was an expanding universe that would keep expanding forever, but slower and slower. So in a universe with just gravity and just stuff, this is what would have to happen, because gravity would slow down the expansion and either cause it to collapse or keep the expansion going, but slower and slower and slower until in the far distant future, the expansion was almost zero. And I'll use another analogy here. And this is a person here throwing balls in the air. So in that first instance, we'd have what we usually see when we throw up a ball. We throw up a ball and it comes down. That's like an expanding universe that eventually collapses in on itself. You throw something up, it comes down. The second possibility is you have a ball thrown up and it keeps going away slower and slower and slower. Now, none of us are strong enough to do this, but if we were strong enough, we could throw a ball up and it would eventually go into orbit. So it wouldn't come back down, but it would always be pulled by the Earth and slowed down by gravity. So about 25 years ago, some of my colleagues were trying to measure which of these two scenarios was occurring, and they found something completely different. They found that the universe behaved as if you threw up a ball, and instead of slowing down or coming down, it went away faster and faster. What they found is the expansion of the universe was not slowing down. The expansion of the universe was speeding up. This third possibility on the right. So they found that as time went on, the expansion of the universe sped up. And nobody had any idea why that would be. That was a very counterintuitive finding, but several groups found it at the same time. And we've got a lot of, in the intervening 25 years, a lot of confirmation that in fact, this is what's happening with the universe. And since we don't really know what's causing it, we give the name to our ignorance of what's causing that. We give that the name dark energy. So dark energy is whatever is causing the accelerating expansion of the universe. Now, if we go back to Einstein's field equation, where we have gravity and stuff, now we have to add something to this equation to make a universe that has something that's pushing things out, the dark energy that's causing the expansion to accelerate. Turns out, the thing you add is this cosmological constant. And so in 1998, when the accelerating expansion was discovered, people said, okay, we do need that cosmological constant. It is the thing that makes the equation work and explain our universe. And several people, three of my colleagues went on to win the Nobel Prize for this discovery in 2011. And Einstein's biggest blunder went on to win a Nobel Prize. So we could all be so lucky that the biggest mistake we make in our life is a Nobel Prize worthy mistake. So that's a little bit of the history of dark energy. And so let's have a bit of a recap of dark matter and dark energy here, the two phenomena that I'm talking about. So I think there we go. So dark matter and dark energy. So dark energy is a repulsive force that tends to push things apart. while dark matter tends to attract things via gravity. Dark energy affects the speed at which the universe expands, and dark matter affects how clustered things are together. And in essence, dark energy wants to push everything in the universe away, and dark matter wants to pull everything together. So these are competing with each other in a sort of push-pull. And that's what we're going to measure with a telescope like the Nancy Grace Roman Space Telescope.
Question.
Yeah.
For dark matter, you clearly showed the iceberg, that there was this dark matter around the observable part of the universe, the galaxies. Is there such an analogy for dark energy? Is it centralized? Is it coming from one place, or is it all over? What's the analogy for dark energy?
So we don't have a good analogy for dark energy. And partly that is because our understanding of what dark energy is so poor right now. There's lots of different explanations for what dark energy might be. Most of those explanations have what we call isotropic. That is dark energy that's the same in all directions and sort of smooth across the universe. But some of them don't have that. And so we might see more dark energy in one direction and another. And that's something that we're going to have to measure with these future surveys, including the Nancy Grace Roman Space Telescope, to better understand dark energy. Another way to put that is our knowledge of dark energy is not yet very well constrained by observations. We know it's there, but the detailed properties, we don't know it's there. And that means the theorists among us can go wild with theories, and it's up to us observationalists. Well, it's up to us observationalists to say, okay, we're going to build a telescope that's going to rule out some of those theories.
Okay.
So how are we going to measure dark energy? And we're going to use this same weak gravitational lensing technique. So I'm showing a recap here. This is a very stylized and exaggerated view of what gravitational lensing does. If you look at this movie on the left, we have the distant galaxies. The light comes through the dark matter to us from the distant galaxies, and we see the changes in shapes of those distant galaxies. And about 17 years ago, some colleagues of mine at Caltech, we used the Hubble Space Telescope to make these weak gravitational lensing measurements over a tiny area of the sky, 2 square degrees, about the size of the full moon on the sky. So it was a tiny part of the sky. And that's what I'm showing here on the right. And using that, we were able to detect and map out where the dark matter was. And we were able to do that at different times backward in the universe. And we were able to show how the dark matter became more clumpy over time. And that dark matter becoming more clumpy over time, how that evolves is it's an interplay between the attractive force of the dark matter and gravity and the repulsive nature of the dark energy. So we're going to use this technique with the Nancy Grace Roman Space Telescope to study dark matter and dark energy that we proved out 15 years ago with the Hubble Space Telescope. So let's see. So I'm going to talk now a little bit about the Nancy Grace Roman Space Telescope. This is a space telescope that's the same size mirror as the Hubble Space Telescope that we've had for 30 years. But as I'm going to show you in a second, we've had a number of advances, the most critical of which are advances in detectors over time. And so instead of a very tiny camera, which was what we have on the Hubble, that only allowed us to look at about the size of this full moon on the sky, 2 square degrees, the Nancy Grace Roman Space Telescope has a camera that's much larger and is going to allow us to look at about 2,000 square degrees of the sky. So about 1,000 times more of the sky than we will have been able to do with Hubble. And the reason that's important is just what I talked about when I had that analogy with the penny in my bathtub. If I look at 1 or 100 or 10,000 galaxies, I don't learn that much about the properties of the dark matter or the dark energy. But if I look at 1 billion galaxies, which is what we're going to do with Roman, then I'm going to learn quite a bit. So I'm going to take a detour here and talk about why are we naming this telescope Nancy Grace Roman? Well, Nancy Grace Roman got her PhD in astronomy in 1949. She became NASA's first chief astronomer in 1959. And for those history buffs, you may recall NASA was formed in 1958. So very soon after NASA was formed, they realized we need somebody to lead our astronomy program, and she was the right person. She championed the idea of large space telescopes that go above the atmosphere and allow us to have very crystal clear pictures. And she was considered in her career the mother of the Large Space Telescope. And the Large Space Telescope, when it was finally launched in 1990, was called the Hubble Space Telescope. So I think these, of course, are fantastic achievements, but can you imagine being memorialized in a Lego set, which is what we have. And so there's some writing there. My employer said you have to make sure to tell people you're not endorsing Lego or Lego sets. So there's some legalistic writing there. But I will say I do have 4 of these Lego sets. And one of the things that really excites me is the middle picture there is Nancy Grace Roman with the Hubble Space Telescope. But keep in mind, the Roman Space Telescope is about the same size as the Hubble. So I'm sure you could imagine taking a few pieces off, changing a few things, and have a Lego set where Nancy Grace Roman is with the telescope named after her. So how does a Roman do this amazing science? So this is a picture of the Andromeda Galaxy, the nearest galaxy to our own Milky Way. And about 5 or so years ago, somebody took the Hubble Space Telescope, said, I want to do a survey of this galaxy. Took them 400 pointings of the telescope to do this. With here it's called W first. That's an old name for Roman. I should get them to update this video. But the Roman telescope will allow us to do this same survey that took 400 times pictures with the Hubble, would allow us to do the same survey in just 2 pointings. And the reason it can do that is it's got a huge camera. So this is the layout of the camera, this sort of Space Invader type. For the older among you, it looks sort of like one of the evil things in Space Invader. But this shape is the shape of the camera with about 300 million pixels in it. And then in the inset in the center, that's the size of the camera on the Hubble Space Telescope. So the real heart of the Roman Space Telescope is its amazing camera, which if you are following space news, there was a news article just yesterday that this amazing camera was sent out to a contractor to be finished yesterday. So this camera is nearly finished, and we've got some of that work going on. And if you remember earlier, you could see that shape of that camera being advertised on my daughter's chest. So that's how we're going to use Nancy Grace Roman Space Telescope to measure dark matter and dark energy. And now I'm going to take a diversion.
So before you go there, there is a question.
Yeah.
Can James Webb Space Telescope provide more information about dark energy? What are the technique features? What are the unique features of the Roman telescope? So a little bit asking about JWST.
Yes, so JWST, of course, is NASA's most recent flagship mission, launched in December of 2021. And it's got a much bigger mirror than Hubble or Roman. But like Hubble, it has a camera that only looks at a very small area of the sky. So over the course of its 30-some-year history, Hubble has looked at about 50 square degrees of the sky. Roman will do that in a few days. So James Webb Space Telescope similarly will, over the course of its lifetime, look at maybe a few tens of square degrees, much deeper and with much higher resolution than Roman or Hubble can do, but it won't ever be able to look at huge areas of the sky, which is what we need to study dark energy.
So the Roman has much wider field of view.
That's right.
And the science is in part getting the large numbers of data points, so you can do different kind of science by having a much larger population, just like your analogy with a penny.
That's right. And so both telescopes, both types of telescopes are needed. If you have one object or a few objects and you say, I want to understand these objects very well, it's great to be able to go after them with JWST. If you need to image or take spectra of 1 billion objects, you need a telescope like Roman. You just can't do that with the JWST.
There was another question going back to dark matter. When Hubble observed the expanding universe, can you just reiterate that this was observed in all directions? Was the expanding, or even with dark energy, is the expansion and the increased expansion equal in all directions?
Yes. So wherever Hubble looked in the sky, he found the same result, that the galaxies were moving away from us. Of course, how the Earth works, Hubble, sitting here at Mount Wilson, could only see the northern hemisphere, but we've since built lots of telescopes in the southern hemisphere. And so we've got a good coverage of the entire, what we call celestial sphere. And indeed, we see that the expansion of the universe is happening in all directions.
Wonderful. Exoplanets.
So I'm going to talk now just briefly about exoplanets. Exoplanets are planets outside of our solar system. And I'm going to show you a plot that when I started graduate school in the 1990s, people were just starting to discover exoplanets, and there were just a few. And over time, people discovered more and more exoplanets, planets outside of our solar system. And this plot, I love the way that this plot shows it, because there's different techniques that people use. And you can see a huge jump when NASA launched a mission called Kepler. And in fact, the scale of the plot had to change to allow all the Kepler discoveries on there. And NASA launched another mission called TESS a few years ago. And as of 2 weeks ago, there were about 5,000 exoplanets discovered. Now, almost all of these exoplanets have been discovered through what we call indirect techniques. We're not seeing the planet directly. We're seeing evidence of the planet by looking at a star. We see the star wobble, or we can see the star blink, and this tells us that there's a planet there. So very few of these planets have actually had images taken of them. And so the blue here is planets viewed in imaging, and so that's a very small slice. And if you can imagine wanting to know that there's a planet there, these other techniques are fantastic, and they're allowing us to really understand how many planets there are. We now know that planets are nearly ubiquitous around stars. Nearly every star probably has some planetary system. On the other hand, if you want to study the planets themselves in detail, you need to be able to take a picture of the planet itself. And so one of the first people to suggest using a telescope in space, or perhaps the first person, as far as I know, to use a telescope in space to directly image planets was in a paper by Nancy Grace Roman in 1959. And one aspect I really like about this story is it was only after NASA decided to name the telescope that I'm working on after Nancy Grace Roman that somebody went back and looked at all of her papers and said, oh, wow, she's also wrote a paper on one of the key techniques that this Roman telescope is going to use to study planets. And she was the first one to do that. So she really was an amazing person and an amazing scientist. So how would you do this? So conceptually, it's quite simple. You use something called a coronagraph. And I'm showing in this video a planet that looks like our Jupiter. And if you put that planet next to its star and tried to image it with a telescope, the planet itself would be completely lost in the glare of the star. You can't see the planet itself. And that's what we're seeing at about this point in the video. You wouldn't be able to see the planet. So what you do is you take an occulting disk and you put that disk in front of the star, and that blocks the light from the star and allows you to see the planet. Now, conceptually, this is very simple. And in practice, it's very, very challenging to do this. So let's see. So I'm going to show this video that shows a little bit of why this is so challenging to do this. And this is a video that NASA put together that shows how a real coronagraph would work in space. So the light from this distant star and planet come into the telescope, and you see some imperfections in what we call the wavefront. It's not a perfectly flat wavefront. That's because there's always imperfections in any mirror in a telescope. So the first thing we do is we put in a disk that scatters the light to the edges of the image, and then we put in something that stops that light, and the planet light comes in at a slight angle. So that planet light does hit our detector. And so that's what we're trying to detect. But there's always some imperfections. And so what we're doing in the Roman coronagraph, that's the instrument that's going to view planets, we have what's called a deformable mirror, which through feedback and computers is taking out the imperfections in the images that we see. And it's taking out those imperfections in a way that allows us to dive much deeper into the light we're getting and allows us to image planets that would otherwise not be possible to be imaged. And the reason for that is this problem. So let's talk about the problem of, or the challenge of using a coronagraph. So if we think of a sun-like star, and we think of the analogy, the sun-like star is like a lighthouse. Now, if we think of a huge exoplanet like Jupiter, that's about 1 million times fainter than the star, that would be like trying to look for a firefly that is circling a lighthouse quite far away from you. It's a really challenging thing. And this is what current coronagraphs on the ground and space are able to do. They're able to see planets that are about 1 million times fainter than their stars. But by using these deformable mirrors and other new technologies, what we're going to do with Roman is we're going to create a much more capable coronagraph. And it's going to take us a long way towards the eventual goal of looking at an Earth-like planet around a sun-like star. And that would be much more like trying to look at a lighthouse that had a single bioluminescent algae floating near it. So that algae is 10 billion times fainter than the lighthouse. And an Earth-like planet is about 10 billion times fainter than a sun-like star. And that's our ultimate goal. So the Roman coronagraph, and this is a fairly complicated plot, but let me step you through it. The Roman coronagraph has a number of new technologies that's going to make it 1,000 times more effective, 1,000 times more powerful than current coronagraphs. And there's about 4 new technologies, including these deformable mirrors and a few others that we're going to test for the first time. And what we are doing is in the upper right-hand corner of this plot, that's the performance we see from coronagraphs today. And the vertical on this plot is the flux ratio, the ratio between the starlight and the planet light. And this is a logarithmic plot. So every step you have there is a factor of 10. So every step in that plot. And the horizontal axis is the separation between the star and the planet. The further away the planet is from the star, the easier it is to see because it's not lost in the glare. So where we are today, that's what current coronagraphs on the ground and space can do. So Roman is, we're building a coronagraph that's going to be about 1,000 times better than those coronagraphs. And that will put us sort of in the middle of this plot. And if you look at the lower left edge of the plot, that's really the holy grail for NASA, looking at an Earth-like planet around a sun-like star, because if we're able to do that, we would likely be able to detect signs of life on that planet, if there is life on that planet. So what we're doing with Roman is we're testing out a number of new technologies on this coronagraph instrument that's being built right at JPL that we hope will allow us to sometime in the future with a new telescope be able to build a coronagraph that's about a factor of 10 better than Roman, and then would get us to that 10 billion to 1 ratio and allow us to look for life or signs of life on planets around other stars near us in the our galaxy. So Roman is a telescope that's being designed to answer some of the biggest questions, not just in science, but I think some of the biggest questions for humanity. That is, what is the universe made of? What do we know about the dark matter and dark energy? And are we alone in the universe? Is there life out there? So Roman is taking us closer to being able to answer these questions. And so that's why I'm really excited about this mission. We're about 4 years away from, 3 or 4 years away from launching this mission. And I hope that you can learn a little bit today, and you'll keep me in mind for a future talk when we finally do launch Roman, and I can come tell you about some of the exciting results in dark matter, dark energy, and exoplanets.
Wonderful, wonderful. What a brilliant presentation. And I'm so delighted. The Roman Space Telescope is not only looking at the universe, but also within our galaxy, looking for exoplanets. So it's both broad, looking at dark energy, dark matter around the universe, but also focused in our own Milky Way galaxy, looking for those exoplanets where possibly we can find Earth-like planets and maybe signs of life.
We hope so.
Yeah. Jason, thank you so much.
Yeah,
This has
thank
been a
you, Leon.
wonderful presentation. Let's give a big applause. And to our audience, thank you for your attention. Live from Mandala Space Ventures in downtown Pasadena. Thank you all for coming here. There's a nice audience here in inside Mandala, and thank you all for listening. Till next time, we'll see you soon. Thank you, Jason.
Thank you.